So we'll look at some specific aspects of monsoon. Since we talked a lot about various aspects of climate change, we can see what specifically may be happening within the Indian region itself. We looked at this and the animation, and we said the ITCZ is to the south in the winter months, or boreal. Technically you should say boreal winter because it's northern winter, and during our boreal summer months it's way to the north. This looks kind of nice and simple, but within this we said when the sun is to the north, land should heat faster, ocean should heat slower, so it should give you a meridional temperature gradient. Low pressure, high pressure, add your Coriolis and you're going to get your monsoon circulation. It turns out that the ocean is warm, so the ITCZ is not this simple in structure over the Indian Ocean, which makes for some interesting problems or challenges. And this is the circulation in winter months and summer months. So you have the sea surface temperature in colors. This is the precipitation scale. This is the temperature scale. You can see that whether you look at it in winter or in summer, the temperatures are 29, 30 degrees over a large part of the Indian Ocean. And we said there is a convective threshold at which ocean heating can create rising air, convergence, rainfall, and so on. So in the winter month, the cooling and the high pressure here, the heating and the low pressure here, you're going to have flow going this way, add Coriolis, so you get northeasterlies. And we know that during the northeast monsoon, mostly some part of Kerala, Sri Lanka, and parts of Tamil Nadu get the rain. During the summer months, you have complete reversal of the circulation. So you have southwesterly winds, and there is some complications. The winds go around and come back over here. These winds, which are the mean winds, are going to go over the Western Ghats. Obviously, you are going to rain a lot over here. This is millimeter per day, so you can convert it into total rain. It will be like more than 2 meters, sometimes 3 meters of rain over some parts of Western Ghats. And you have the Himalayan foothills, which also gets the monsoon trough and the rain, which can be as high as several meters in Cherrapunji and so on. And you have the core monsoon zone, which is what we typically refer to as the monsoon zone, and that is getting around 900 millimeters. So there is some relation between the north-south distribution as well. And you have these Burmese mountains. So there are lots of details here that you can look at. We have the African highlands here, which we briefly looked at. You have the Himalayan mountains here, and you have the Burmese mountains here. So you have some kind of an envelope here that's happening. So the cold temperatures are here are related to what? The upwelling. So you have along-shore winds which are pulling the water away from the coast because of Coriolis. So you have cold water coming up. So you will see soon that the ITCZ actually, you cannot see it here. We'll see it in another plot. The ITCZ breaks up here. The winds here remain largely southeasterly, so they are like the trade winds in the other ocean. It's the northeast that is, it's the northern Indian Ocean that's different. So you have kind of northeast trades here, but the ITCZ is not similar to other oceans, right? ITCZ here is got southeast northeast convergence, whereas the Indian Ocean is different, and of course the southeast is very different. So you have to understand the mean circulation and the fact that land is warming and the ocean is warming. And we said because of aerosols, maybe land is not warming as fast as it should because of solar dimming and so on. Then the question is, with global warming, what is happening to the monsoon? So if you look at the mean rainfall, this is the winter months. Obviously you have negligible rain here which doesn't show up. This is the 10 millimeter per day contour, and you have Amazon rain which happens throughout the year. You have some rain over Indonesia that happens throughout the year, with less in the summer, more in the winter, and so on and so forth. But here you can clearly see that you have rain over the ocean and over the Bay of Bengal and Western Ghats and Arabian Sea, and the ITCZ is broken up here because of these cold temperatures, right? So this is an interesting problem. Most of you probably know that when we say all India monsoon rainfall, we average this and say that hardly ever varies more than plus minus 10%, and mathematically maybe that is because you have this kind of bucket here because of this African highlands, Himalayan mountains, Burmese mountains, and the ocean. So I suspect if you average over this whole box, that varies even less than 10%. So the main point is that even though here we say ITCZ moves north, because the ocean is so warm, the convergence over the ocean still happens. Okay, so this marine ITCZ doesn't disappear, and the rainfall is not maximum over land. It's actually maximum over the ocean here and maximum over the ocean here. And there is nice study by one of my students, for example, to show that as the winds approach here, they have to climb the mountain. And as they begin to climb, they slow down here and the ocean warms. So it's the ocean that controls the rainfall in this place, whereas this is always warm. You can see that this remains fairly warm. So this rain is controlled by the atmosphere. So the atmosphere has instabilities and so on. So it doesn't mean ocean doesn't have a role. It's just that ocean, as long as the ocean remains above the threshold of 28 degrees or so, the small variations in SST don't matter. So I'm always a bit concerned about the emphasis on ocean processes in studies like OHM and so on, because I think the rainfall processes here are mainly controlled by the atmosphere, not so much by the ocean. This also shows up that when you improve the SST predictions here, the monsoon doesn't really improve because you are already above the threshold. Very little of the variability is actually controlled by the SST. It's the atmospheric processes that control the monsoon. So there's those kinds of details. If you then average the rainfall over this Indian band of 75 to 80 longitude band, 70 to 95, and over the so-called maritime continents, these are called maritime continents. So if you look at rainfall over here and rainfall over here, you will see that the seasonal evolution with latitude, sun is to the south, so the ITCZ is to the south in both places. So this is over the Indian Ocean, this is over the maritime continent. As sun begins to move north, ITCZ moves north here. Maximum rainfall moves north. There is rainfall here, but maximum convergence has moved clearly to the north over to the Philippines and so on, Borneo and so on. Whereas here, it begins to split. Okay? So this split actually happens earlier in March, April. By the time May comes, the ITCZ is split somewhat. So there is a convergence zone over the Indian subcontinent, what we call monsoon trough, but the marine ITCZ also still remains there. Okay? And we are always focusing on monsoon onset as the rainfall over Kerala. This is something we are obsessed with. Next week there is a meeting at IISc trying to see what onset really means, and I have always pushed to say that this is where the onset actually happens. When the ITCZ, it wants to move north, but the ocean has a control on it, so there is always this kind of a battle that happens. So there is this back and forth or the split, and then eventually it splits into two. But Then there are, because of the way ocean circulation and atmospheric instabilities and so on work, you have what are called depressions, cyclonic systems, mesoscale eddies, and so on, that are going from there to there. Okay? Those are the ones that create what we call active and break periods. So if you think about the monsoon, it doesn't rain all the time. It rains for a few weeks, and then it stops for a few weeks, and it starts again, and so on and so forth. In a monsoon season, you will have, on average, 3-4 active periods and 3-4 break periods, which is related to this. So when you think about the circulation, then you have to think about the mean circulation, which is bringing most of the moisture. So moisture, almost 70% comes from here, another 30% gets picked up here. That latent heating cools the Arabian Sea, which includes along-shore winds and the upwelling. And we said there is also some complicated upwelling happening here, which maybe not everybody remembers, but there is a very strong relation between the strength of this so-called low-level jet or the Findlater jet, which is this southwesterly wind, almost westerly wind, and the amount of rainfall. So if you look at the wind stress curl, if you use your right-hand rule, it is downwelling on this side and it is upwelling on that side. It is in that direction and this direction. So when it gets stronger, you get stronger downwelling here and stronger upwelling here, and so on, which matters on longer time scales. But nonetheless, some of that jet crosses over and then curves back, and that's what gives you this cyclonic circulation, which is important for low pressure, rainfall, and so on and so forth. So there is a mean circulation, which is bringing a lot of moisture over, and there is also this back circulation, which is bringing a lot of moisture from the Bay of Bengal. So in fact, I think one of Rama's students is trying to see what is the direction of winds when it rains over Bengaluru. So if you look at Bangalore, and Chennai, they are all at almost the same latitude, but Chennai gets no rain in the summer. Most of its rain comes in the winter months. Why is that? Maybe there is a wave getting set up by these winds going over the mountain, and there is an example that works over the Rocky Mountains. It turns out that the wave over the Rocky Mountain actually affects climate over Europe, for example, okay, and so on. So those are kind of the details you have to worry about when you worry about impact of climate change on the monsoon. So it's not just ocean heating, land heating, but also how the amount of rainfall changes, because that's the heat source, which means the winds will change because the winds are responding to the heat source. And if the winds change, the amount of moisture supply changes, hence the rain changes, and then the heat source changes. So there is a very strong feedback between the thermodynamic component, which is just the humidity change, and the dynamic change, which is the wind change. They are very closely coupled to each other. The other detail is that even though we keep saying monsoon is like a land-sea breeze and it depends on ocean heating and land heating and so on, once the rainfall starts here, this massive heat source, and when it rains heavily, it actually brings down the dry, cold air from the top. So oftentimes when it rains, it cools by a lot, several degrees. Right? That is what leads to actually general cooling of temperatures over India. So Delhi, they will be baking in 40 degree, 45 degree, 50 degree heat before the monsoon, and they say as soon as rain arrives, it will cool down. Basically because you are bringing massive amount of cold air from the top.
Is it only cold air, or is it also the cooling effect of evaporation of the water that falls?
What do you think?
Should be both, I mean, but it seems that the cold air is a bigger thing.
During the rainy season, you think there will be a lot of evaporation?
There is always humidity. I mean, if there is water, it will try to saturate the.
If it is raining, is it already saturated? You just think intuitively back of the envelope that 10 degree cooling you cannot get from evaporation. So it will be very small compared to amount of air that is coming down, okay? And it's the rate of cooling as well. Evaporation is not as fast as rain, right?
So it so happens that some initial rain actually makes it even warmer in there. And then once it starts raining,
it depends on how, yeah. So if you start with, if it rains for a few hours during the day, like it has a diurnal cycle, it'll warm during the morning and then rain and cool and then again it'll warm. So unless the rain persists for days and days, it doesn't cool down.
Yeah.
So you need the continuous pull down, okay? The diurnal cycle is very strong on land, obviously, because sun comes up, you heat it up, and then sun goes down, you cool it down. So nonetheless, it is this heat source that is going to drive the monsoonal circulation. So it's as if there is, once it starts raining, it is going to demand more moisture, and it keeps on getting the moisture from the ocean, from this side and this side, which means that it is not now the ocean land temperature contrast that is driving the monsoon, but it is actually the tropospheric temperature gradient that is driving the monsoon circulation. So that is looked at from what is called 800 hectopascal to 200 hectopascal. So basically, if you remember that the pressure drops logarithmically with height, so you have some upper level like 200 hectopascals, which should be actually pretty close to the tropopause, and 800, which is pretty close to the boundary layer or the frictional layer. And that gradient, there are other indicators of moisture supply, moisture transport, and so on and so forth. Nonetheless, if you look at the temperature gradient, you look at the northern box minus the southern box, which is randomly defined based on some things which we are just showing that is actually maybe a little bit wrong. Nonetheless, you look, the gradient is negative till the monsoon onset happens, and it remains positive during the monsoon season, which means this box is warmer than this box during the monsoon. And when the monsoon withdrawal happens, that gradient again becomes negative, right? And obviously you want to understand immediately what are the relations. We said, did we say that El Nino affects the monsoon? What did we say? So in general, El Nino tends to reduce the monsoon, seasonal amount of rainfall, and you can see every day now there is a discussion in the news about what this monsoon will do, because there is some form of El Nino that's trying to happen in the Pacific. But if you are already knowledgeable about El Nino and monsoon, one thing you should remember already, when does the El Nino peak? Same winter? As same winter means what?
Winter.
And when does the monsoon peak? Okay, so it's not the same, it is, one is 6 months before the other, right? So if El Nino has to impact the monsoon, but El Nino is peaking in December, January, February, but monsoon is happening in June, July, August, then you have to be very careful. Immediately that means that unless the El Nino has become quite strong by June, July, August, it is probably unlikely to do something to the monsoon. So it shows up that in the correlations that only about 50% of the droughts are actually explained by El Nino. Then the question should be, what is El Nino? If you want to think about it as a heat source, what is El Nino doing?
Distributing the heat over the surface.
It is shifting it eastward and redistributing it globally as well. And monsoon is also a heat source, right? So obviously monsoon also can affect El Nino, right? This is one of the big open questions. What can the monsoon do to the El Nino, considering it's happening 6 months before? If the El Nino is weak, can it kill the El Nino? Some people say abort the El Nino, but considering El Nino is Christ's child, we may not want to abort. Christ child, but nonetheless. So essentially, you want to think about how El Nino and La Nina affect the monsoon, and you can see that there are subtle differences. Maybe on average, the onset is happening a little earlier in La Nina, and withdrawal is happening a little later, and maybe there is a little bit more rain. So small changes, and it turns out that in general, if the onset happens earlier, you tend to have excess rainfall. Again, not 100% of the time, but when the onset is late, the chance of having an excess monsoon season is almost zero. Okay, so you have to just worry about correlations to say what they actually mean. So that's in the mean sense. Other way to think about it is that we said southern oscillation of El Nino is pressure over Darwin minus pressure over Tahiti, and so the correlation of the Darwin pressure extends over here, doesn't cover all of India. So when El Nino happens, this pressure changes, hence this circulation changes, and the correlation is not perfect, but there is a large scale relation through this Darwin pressure and so on and so forth. But people think about it as also waves, because every time you perturb the heat source in the atmosphere, it sends off waves, right? In what? This one? This is called hectopascal, or you can think of it as, yeah, whatever. Okay, decibars, millibars, so on. There's multiple units. So if you take that into account and look at the seasons for 3 different years, this is looking at 1972, 1994, and 2002. And the envelope shown here is the climatological rain, which starts somewhere on June 1st and ends around mid-September. IMD has just announced that it's going to change the definition of the season and the amount of rain and so on and so forth, because there are trends, etc. But you can see that this one was 1972 was an El Nino year. This was an El Nino year. This was kind of a mild El Nino year, but Indian Ocean was doing something else. So you can see that when it is below in red, that means there is no rain. When it's in blue here, that means it's raining. So these are the break periods and these are the active periods. You can see that this year had only about 700 millimeters of rain. This one had more than 1,000, and this one also had only 640 millimeters of rain. So these are drought years, and this is a normal year or a wet year. And you can see that the distributions are different in a wet year compared to a dry year. Which means what? If this is the active period, this is the break period, you can see visually that maybe anecdotally we can say that there are more break periods, longer break periods during a dry year, maybe an El Nino year, and there are more wet periods and longer wet periods and shorter break periods, active periods and break periods during a normal year or a wet year. So this is only averaged over the core monsoon zone. So we are looking at seasonal mean rainfall, all India rainfall, or we are looking at core monsoon zone and so on and so forth. So various quantities get looked at, but what you have to think of is the length of the rainy season. So onset happens, withdrawal happens. There is a length of the rainy season, which is a certain number of days. Within that, you have number of rainy days and amount of rain that falls. Okay, so with El Nino or global warming, you have to worry about how the length of the rainy season may change and how the number of rainy days may change and how the intensity or how much it rains on those days may change. It matters because for a farmer, an even distribution of rain is much preferable than even if you get 1,000 millimeters, but if it rains in 30 days instead of 90 days, that's going to be a disaster, right? So there is the onset because that sets the crop calendar. They want to prepare the land, they sow the seeds, etc. And each crop has a growing length, harvesting time. And onion, for example, you don't want it to rain when it's getting ready to be harvested, then it'll get spoiled in the ground, peanuts, so on and so forth. So the distribution of rain is very important. So length of rainy season is important, number of rainy days is important, and length of rainy season and number of rainy days together with the total amount of rain obviously will determine how much it rains on those rainy days, right? If you have fewer rainy days, then it'll rain more if the rain is larger. You have a question?
Yes, sir. If you compare 72 and 2000, 72 has a very late onset, but the withdrawal has been around normal time. And in the figure previous, which is not a hard and fast rule, that if it is early onset, it tends to be a later withdrawal. But this is a drought here.
No.
In 2002, it is a normal onset, but the withdrawal is quite early.
First of all, it's just getting cut off here. It's some determined onset doesn't always happen on June 1. So you cannot say early onset because everything is on June 1. You are saying this is starting with a break.
There's no blue region, so it can start.
So that is another question, right? You have to ask, what does onset mean? If it didn't rain till here, does it mean monsoon onset happened here or it happened here?
Well, according to the definition of the dry spell, you will not call it a dry spell if it has not started.
Right? So, first of all, you have to look at the whole year. I'm just showing this as an example because it's possible that it rained in May and didn't rain in June. In Bengaluru, it rained, I think, a lot in May, and now it has not rained for some time. So, I'm trying to make a few points, but don't extrapolate too much.
But would it be called pre-monsoon shower and not monsoon shower? If it has rained in May, then
but that is still the point of deciding what is onset, right? So, first of all, I didn't say if early onset happens, withdrawal will be late or whatever.
No, it was just shown in that correlation
I said,
diagram, most cases.
No, where was it?
Nino is late onset and early.
Yeah, I think what I said was, in general, less than 50% of the time, early onset tends to give more rainfall. That doesn't necessarily mean late withdrawal. You can get more, so this is showing the same period but showing more than 1,000 year and 691. Okay, it's not just, onset is not related to withdrawal. Onset is generally related to total rainfall. If early onset happens, then usually means 50% of the time you will get more rainfall. But that doesn't mean late withdrawal. I'm just making points about onset and withdrawal and active and break because you want to, under global warming, you want to see what happens to onset, what happens to withdrawal, what happens to rainfall distribution, and what happens to active and break periods. Will it rain? You can, for example, this one is not giving you a very clear sense of whether it rained less because it rained fewer number of days or it rained less on the same number of days. Remember, this is not zero rain. This is just less than normal rain. So it has a break period over core monsoon zone, but it will be raining somewhere else. Okay, so it's complicated. Just remember that there is onset, there is withdrawal, hence there is a length of rainy season. There are active and break periods, which means there are number of rainy days. Everything can change. Number of rainy days can change, or number of rainy days can remain the same, but amount of rain on those days can change, and so on and so forth. So all those things have to be kept in mind. The other thing to remember now, to connect the seasonal rainfall to the what is called intra-seasonal rainfall. Season is considered 3 months, 90 days. Intra-seasonal is anything less than 90 days, less than a season, shorter than a season. So typically you split them into synoptic time scale or weather time scale, which is day 1 to day 10. Intra-seasonal time scale goes typically from day 10 to day 90, but sometimes day 100. and then seasonal is longer, interannual is longer, and so on and so forth. To relate the two, you have to just now comprehend that you have the southwesterly winds, which are the mean winds. They will be there all season long. They might get stronger or weaker with active and break periods, but they will be there all the time. We also mentioned a marine ITCZ and a monsoon trough, right? So what is happening during active and break periods within that is when there is an active period, there is convergence and rising motion over the subcontinent, over India core monsoon zone, and there is a sinking motion over the marine ITCZ. And vice versa. If there is a break period here, then there is convection happening here, rising motion here, and sinking motion here. What would this circulation be? Meridional overturning. Meridional overturning is good, but it is from the ocean. What was the meridional overturning in the atmosphere? Idli. So, Hadley cell, this is called the local Hadley cell. When we looked at the Hadley cell, we made the zonal mean, we averaged all the longitudes and said there is rising motion and there is sinking motion. The sinking motion is generally over deserts. And because of the monsoon, we are not a desert, we are, even though we are in the subtropics, we are actually getting plenty of rain. So this is the local Hadley cell, okay? So that is doing a back and forth. So that, how does that work? If you start with a break condition at time t0, here you are around 5 south where the SSTs are warm, and which means convergence, so the thermocline is deeper or sea level is higher, and you have rising motion, so you have rainfall and convection over the ocean, and you have local Hadley cell sinking over India at around 20 north. And after about 10 days, there are waves, intraseasonal oscillations, cyclonic systems, mesoscale eddies, many terminologies, but something transitions towards the north. So the convergence zone is moving north, and it's raining here, it's partially sinking here, it's sinking here, it's still sinking here. In about 30 days, you have 20 days, you have moved here and you are raining over India, so you have an active period, and now you are sinking over the ocean, and then you go back towards the ocean. So this is kind of a 10 to 30 day cycle, or 30 to 60 day, depending on these various time scales we see here. So this is 30 to 60 days, this is 10 to 20 days. So there are multiple time scales at which this kind of a northward propagation, it is called. So the system is moving from the equator northward, okay? So those are also referred to as mesos or monsoon intraseasonal oscillations. Sounds like a Japanese soup, but it is an Indian soup, okay? So that is the multiple time scales that are involved. So weather time scale is there, in the sense there is diurnal cycle. In Bengaluru, for example, it typically rains around 5 p.m. or something. In Delhi, it will be maybe around 2 p.m. or something. In Mumbai also it is at some, so land has strong diurnal cycle, which is a weather time scale, but that is happening in the envelope of intraseasonal time scale, and then there are seasonal time scales. So we want to understand what is happening to the monsoon under global warming, right? So this is the map we looked at. We said Indian Ocean is warming fairly monotonically and rapidly, and so is the West Pacific. So when we talked about Haiyan getting stronger than expected, it is because of this very warm water. There are dynamic arguments as to why these are warming faster, and we have already talked about this not warming as fast because of the thermohaline circulation and so on. But this is the annual mean trend. So you need to actually look at the seasonal trend, which I don't know if I have. I should have had somewhere. You have to look also at potentially the June, July, August trend, or maybe even March, April, May trend, because the monsoon circulation begins to get set up during March, April, May, right? So you can look at seasonal trends and you will see that during June, July, August, Western Arabian Sea is warming almost 40% faster than the rest of the world. Again, because of dynamic reasons, this happens. In general, Indian Ocean warming is related to multiple things, obviously atmospheric circulation and wind changes, which itself would be related to monsoon changes and so on. But you are also getting some water through here, which we called what? Anybody there? What? Do we remember why water was going this way?
The rising water from the below.
It was part of the thermohaline circulation, right? So thermohaline, the only tropical interbasin link of the thermohaline circulation is here. It goes then around here and then goes back to here, right? That is called the Indonesian through flow, okay? So Indonesian through flow, which is bringing warm water from this side into here, is putting in about, we didn't introduce these units, I think we did maybe somewhere between 1.5 to 1.5 petawatts, which is, peta is what? 15, 16, 12, 13? Giga is 9 and peta is? Giga is 15? Huh? 15. Okay. At least, fortunately, Google is there. We can always Google it. 10 to the 15 watts or so are being brought here. What else can bring warm water into the Indian Ocean? Is there a bus at 12:30? We should let them go, or bus at 1? Anybody know? When is the bus? Okay. So how else is heat? I'm going slow because this is some, even if you learn nothing from the rest of the lecture, at least if you get a good sense of the monsoon, it will be good. You want me to wrap it up quickly, or no? You have to always ask the dean because she pays for all the coffee and everything. How else can heat come into the... From the... What is that? What is that part of? Why is it that? Huh? Yeah, you said it. What? Keywords, huh? We're getting fun. The thermohaline circulation is still, so you have deep water formation going south, mixing here, going here, and coming back, going that way. So it's not warm water that is getting pushed. Deep and intermediate waters are coming from the Antarctic circulation into the Indian Ocean. Because the Indian Ocean is close to the north, that water has to become surface water and then go back out, right? So if you think Southern Ocean is here, the water is coming at deep and intermediate depths and it is converted into surface water and going back south, right? So why did we say Southern Ocean is special? If you're warming the Southern Ocean, what would happen? In terms of vertical distribution of heat, what would happen in the Southern Ocean? We said because it's a channel, it is getting a lot of wind energy, so it is getting mixed a lot. So here, the warming will penetrate deeper much faster than other oceans because the Ekman currents will keep getting deeper and deeper, which means if you warm the Southern Ocean, you are bringing more warm water into the Indian Ocean. And that warm water has to come up. So all those things add up to give you a unique warming of the Indian Ocean. Some heat coming from here, some heat coming from here, all has to become surface water and come out. What is the net effect? You are seeing, I will jump around a little bit, that I will show onset and delay changes, withdrawal changes later on. But if you just look at the last several decades of number of rainy events which have greater than 100 millimeter per day or greater than 150 millimeters per day, and events that have less than 100 millimeters per day, you can see that the number of rainy events with greater than 100 millimeters per day or 150 millimeters per day have increased, and the lighter rain events from 5 millimeters to 100 millimeters per day have decreased, right? So if you are raining heavily here and it needs certain amount of water, then it will start taking that water from everybody around. So you can think of it as a heat source. Once it starts raining heavily, it's a huge heat source. So it will start demanding water, right? So there are lots of details. There is something called precipitable water, which means the amount of moisture that is there in the air column. And it turns out that as March, April, May happens, the water builds up. But when it rains, that water doesn't get spent. It varies only by about 10%. Which means all the rainfall changes are happening because of the fluxes. So when it rains, it is asking for a loan from somewhere saying, give me more water. It's not spending what it has. It has built a saving account and it wants to spend, it makes a loan. This is why evaporation happens somewhere and the moisture flux brings all this rain. That's some detail that has to be worked out, but essentially precipitable water doesn't vary much, but fluxes of moisture vary by a lot, which means that if you rain heavily in one place, you're going to reduce the rainfall in other places. So that would generally at first order explain why when extreme events increase, lighter rain events actually decrease. Okay? What is the pattern of changes? So if you look at the change in the rainfall trend, this is showing wherever it is negative, that is the change over 66 years. Wherever it's positive, it means it is increasing. Okay? So there are a few spots, like here it gets only about 200 millimeters of rain. So when you say it has a increase, that is not much. What is interesting here is if you look at Tamil Nadu, the trend is actually very small, and it turns out that if you look at annual trend, Tamil Nadu is actually getting more rain now, especially Chennai. So rainfall amount has actually increased, but now Chennai is facing water crisis. So you can go and figure out what exactly, how much sambar can they make. Yes.
Isn't that color coding 0 to -1? So it is decreasing.
Where is it? Is decreasing in this place, and here I'm saying in the summer it is decreasing, but in the winter, when does Chennai get most? Yeah, so I'm said annual trend is increasing. Winter rain is increasing. So annually they get about 1,000 millimeters and it is increased. So they have no business having water problems, but nonetheless they are, right? So, and there are many details here. You can see better, you cannot see very clearly here, but Kerala has had a decreasing trend, whereas the northern Western Ghats have had an increasing trend. Okay, so there are other maps which are better, more resolved than this one, the main thing is that the core monsoon zone has had a decreasing trend in rainfall. Okay, and if you look at the frequency of extreme events, this is not a very good way of thinking about it, but these floods over large areas have increased almost threefold. So these events where flooding happens over more than 10,000 square kilometers used to happen about twice per year before about 60 years. They have slowly increased now to about 6 per year. So when you read about floods last week, it will talk a lot about Assam and rhinos and so on. But actually, if you look at the map, it is flooding on a large, very large area. Okay, so
Besides the core monsoon zone, around 1 to 2 millimeters per day.
Per year, yeah.
Per 66 years.
Per 66 years. So the rain,
So
if you spread,
that's close to 200 millimeters.
Yeah.
Over the monsoon.
Or 4-month period. So
That's it.
That's
1/4 of the close to 1/4.
Yeah, there is a 10 to 20.
Years, the monsoon is repeated.
Yeah, I will show I'll show an average. Sorry?
The monsoon hasn't come down from 800 to 600.
In some places it has. 800 is an all India average.
Yeah. And
so if you look at the core monsoon zone, it has come down by 10 to 20%. Okay? So we are saying two things. There is a trend in the mean. So the mean has largely decreased over a large part of India, including over here, for example, with few increases. And it is flooding more on a larger area over this same decades. Okay? So now you have to think onset must be changing, withdrawal must be changing, number of rainy days must be changing. So if you decrease the rain by 20%, but if you squeeze the monsoon season by a certain amount, then you will be raining more during a few days, because floods means essentially you are going to rain heavily on some days, right? So that's what is happening. So this is looking at two products. One is the IMD precipitation, one is the East Anglia precipitation, and it's basically looking at Western Indian Ocean SST correlation with the monsoon. Obviously, trends always correlate, not surprising. And you can see that they have this approximately similar patterns, which means the warming of the sea surface temperature over the Western Arabian Sea has potentially causal correlation with the decrease in the trend monsoon precipitation. Okay, so statisticians will not be very happy with this. First of all, because you are drawing a trend line, which you can always do. But how many of you can look at this and say this is a trend? You can draw a line like this and a line like this and call it a regime shift, that you were in a high rainfall period here with some decadal variability, and you have switched to a low rainfall regime with some decadal variability. Right? This is a debate that goes on, especially because we know that in the 1970s, there was something called a climate regime shift, which is very well recorded in many, many things. It was in fact first found in zooplankton and fish by the Japanese scientists in North Pacific. And they showed that there was a regime shift that happened in the 1970s in the abundance of certain zooplankton, which is the food for certain fish. And that statistical significance has actually not been shown in the climate. Climate community then caught on saying that the regime shift happened. And they have tried to find an explanation for what would cause a regime shift in the climate system. We still don't have a very good solid theory for it. If you look at things like PDO and all, they also have this kind of decadal time scale. But as I said, PDO is not really a mode in the sense of the process that, like El Nino is a mode, we have the Eknes feedback, upwelling, wind feedback, and so on and so forth. And that is not found in PDO. Okay? So the main thing is now if you read the interview by Secretary Rajivan, I think earlier this week, he said we are in a low monsoon regime. And already there is a couple of papers from MIT claiming that monsoon is recovering. Right? What did we say? We said, why did we say there is a negative trend despite global warming? What should happen with global warming? What do you expect?
More water could be potentially being held in the atmosphere. Yeah, there was a very logical reason why it is. Aerosols are one, but this is.
Huh? This is not. Why not? What should happen with global warming for monsoon? Start from there. We said monsoon is related to. So, what should happen with global warming?
The contrast is weakened.
Why did it weaken? What should happen? Don't say what happened. What should happen? Why is everybody struggling? Let's go back to heat capacity. Should ocean warm faster or land warm faster? We are missing the shuttle for nothing. So land should warm faster. Should that make the monsoon stronger or weaker? But we are saying it got weaker because? Huh? Aerosols did what?
Aerosols drizzle, make it drizzle. They don't let a lot of water accumulate. But here it should not be aerosols.
What did they do? Huh? Somebody mentioned something else. We are talking about land. If monsoon decreased means what? We expect that land should heat faster than the ocean, but monsoon has not increased, which means?
Aerosols are blocking the surface.
Which means?
Global warming is not reaching the land. It's not trickling down the land.
It's not trickling down because? Huh? Why?
There is no aerosols. That's how aerosols come out of the ocean.
So what are the aerosols doing on land?
Because we produce them.
No, everybody is laughing, but nobody, unless you can give the answer, you cannot laugh at others, right? So,
more clouds, and that is not.
we said we don't even know cloud feedbacks yet. What did we call it?
Solar dimming. And solar dimming.
Whew. Solar dimming. When we are very dim, sometimes we forget, but solar dimming, we said, is likely cause for land not warming as fast as it should. Hence, the monsoon is not increased, instead has decreased. CCN may be causing drizzle and reducing rain, but the main impact is gradient has actually not strengthened, it is weakened. So if this trend is true, then we are saying aerosols are potentially responsible, but problem is aerosols were not that high here, they became much higher here, and so on and so forth. So there are issues in explaining this. First one is whether this is really a trend or whether this is a shift, and what is the relation between increasing ocean heating and rainfall, and whether aerosols actually can explain the trend. Maybe aerosols were not doing anything here and they became effective here, right? So it is still possible that there is a trend here but not here, which is riding on top of the shift that is natural, and so on and so forth. And the other thing you have to remember is that the warming, we said, accelerated from here on, right? So the question is whether that is related to this or not. So there are too many factors that we have to account for. You have a question? Okay. So that is that. Now, El Nino, maybe we should stop here because even I'm feeling tired of asking questions.